All right, so when we're working with Fourier series, these are functions defined on intervals that are symmetric to the origin. So they're typically defined on intervals between some fixed value L and the negative fixed value of the same thing. So negative pi to pi, or negative 1 to 1, or that sort of thing. And on outside that interval, they're periodic, so they repeat themselves. So this is how we can represent these functions with sine or cosine, because they are also periodic. So as long as we're only interested in a finite interval, we don't really care what happens outside that interval. We're imagining that it's periodic, but really what we're concerned with is what's going on between this period of the definition between negative L and L. Now, when we encounter functions that are not defined on that entire interval between negative L and L, for instance, perhaps they're only defined for half of the interval, say between 0 and L, then we run into some issues because we have to use the definition of the Fourier series, which is defined on an interval twice that long. So we have a couple of options available to us. We want to try to extend our function so that it applies on the entire interval negative L to L, where the Fourier series is going to be calculated. Now, we have a couple of options, and so we're going to go through what some of the options are and what some of those consequences are. Now, it would first appear that the simplest way to extend our function would be simply to set the component that we don't have, that negative L to 0 interval, to be 0. So for instance, if we're working on an interval from negative 1 to 1, and we have x defined from 0 to 1, then we would simply say, okay, well, this is the part that we care about, and we'll just say the rest of it is 0. And then when we go and we calculate the coefficients for the Fourier series, then we run into this issue. So we have our integral. It's defined from negative L to L for our coefficients for the cosine functions. We multiply the function by the cosine, and then we split it into two sections, negative 1 to 0. The f of x is 0 times that cosine, so that will become 0 for the whole thing. Great. But then we integrate from 0 to 1, x times cosine. And so we would get that. Now, the difficulty with this problem is that the function is not symmetric. And when we go ahead and calculate both sine and cosine, we would hope, if we had some symmetry, that we would end up with only the sine or only the cosine integrals surviving. But in this case, the function is not symmetric. And so we're not only going to end up with coefficients for the cosine, we're also going to end up with coefficients for the sine, because the other functions are going to be trying to not just take this section, but they're also going to be trying to cancel out this section. So our repeated wave that Fourier is trying to model is going to be this 0, and then it raises to x, and then it drops down to 0, and then it raises to x again. And so each time when we calculate these non-symmetric extensions, we're going to have coefficients for both sine and both cosine. So our result is going to be much more complicated. Now, if we want to use symmetry, we can actually make our problems a little bit easier, because then if we have only an odd function on this interval, then we will only have the sine function that survives. All the cosines will go to 0. And if we have an even function on our negative L to L, then the sine will go to 0 and only the cosine will survive. So when we have a non-symmetric function, we have to deal with both. But when we have symmetry, it turns out that we only have to deal with one set of coefficients. So it will be more efficient for us mathematically to extend our function from the 0 to L interval in a way that allows us to take advantage of that symmetry. So extend the symmetry to be odd or extend the symmetry to be even. Now we do have a choice. So let's look at extending this one. Since x is already odd, then one option that we have is to simply continue x through that entire interval so that it is defined on -1 to 1. Then all the coefficients for cosine are going to be 0 because this is an odd function and not an even function, and not a neither where we have to do combinations of both. So we will only have to solve for the coefficients that involve the sign. Now, if we extend it as an even function, in this case, since it's x on the 0 to 1 interval, we could extend it as essentially an absolute value on the 0 to -1 interval so that it would look like this. This is now even symmetric. And so now it's the sine coefficients that will disappear, and we'll have only the cosine that survives. So let's look at it in a second example and see what our options are. So again, we have a function. It's defined only on the interval 0 to 2, and the function is 4 minus x squared. So we could, if we wanted to work really hard, thinking that this initial choice would be easier, we could extend it asymmetrically by specifying that the interval between -2 and 0 has the value 0. Now, again, that's going to give us an asymmetric repeating section of the graph. And so we're going to have to live with having both sine and cosine coefficients survive in our final answer. On the other hand, we could continue to make this function, extend it so that it's even. This is 4 minus x squared is already an inherently even function. And so we could just extend it so that it goes not just from 0 to 2, but from -2 to 2. And mathematically, this may be the easiest one since it leaves us with only one integration to do. And furthermore, we could, if we wanted, sometimes we would prefer to work with sine or cosine, in which case that may determine whether we're extending it to be even or odd. In this case, though, we're going to, if we extend it to be an odd function, then 4 minus x squared on 0 to 2, you would have to flip all of the signs, and then this extension piece would be this reverse paraboloid. It would be x squared minus 4 on the interval -2 to 0. Now, again, let's look at one additional example that's a little bit more complicated, where it's already composed of multiple pieces on our 0 to L interval. So in this case, we have x minus 1 between 0 and 1, this one, and then we have 1 from 1 to 2. Now, this doesn't have apparently any inherent symmetry, but we want to impose a symmetry on it, ideally, if we're going to extend it. Now, again, it would again seem as though extending this to 0, and this, again, it's a valid option. You can extend 0 from -2 to 0, and then you would get a graph that looks like this. Now, again, this has no symmetry. When you go and do the integration, the 0 will cancel out, but you'll have two pieces for the 0 to 2 section, and then you will have to do both sine and cosine because the Fourier series will try to replicate this, and since it has no symmetry, it will need both odd and even functions in order to produce this. So another option that we could use is we could try to make the graph even. Now, this extension down here, we could extend that in this direction. Again, think of it like an absolute value from the section from -1 to 0. Again, we would, as we saw with the previous example, we would have to, because x minus 1 is more odd than even, we would have to flip the sign, but the intercept would still be -1. So this line segment right here, we would want to be -x minus 1. So it has a downward slope, the opposite sign of the one that we were looking at before, but it has to go through the same intercept. So we would flip the sign of the odd component, and we would leave the even component the same. And so again, we would have to extend then the constant over here. It would have to be extended also on this interval from -2 to 1. So this is what we would get here. 1, it's even already because it's a constant. So we would extend that from -2 to -1. And then this segment would be flipped over, and that would give us -x minus 1 between -1 and 0. This segment right here is the original x minus 1 from 0 to 1. And then this segment out here is that 1 again. Because we're making it even, it doesn't have to change. And this goes from 1 to 2. And it looks an awful lot like a smiley face. Now, to extend the function as odd, we can do sort of a similar manipulation. Now, recall that when you make an odd thing, that anything that's even has to flip sign. So the 1 from 1 to 2 will get flipped over to be -1, because when you're on the left side of the graph, you have to be the opposite sign of the thing on the right side of the graph. So that flips for the odd function, because you're going from the first to the third quadrant, not the first to the second quadrant. And then this segment right here, in order to flip it over, it can't intersect at -1 anymore. It has to move from the fourth quadrant to the second quadrant. And so what's actually happening now is we're actually changing the intercept, not the slope. So this is the odd component of this section, and the even component is the one that has to change sign. So we go from x minus 1 on 0 to 1, and when we move that into the second quadrant, the graph that we get is x plus 1 from -1 to 0. And so our graph will look like this. And you can see this has odd symmetry. I have the first quadrant mapping to the third quadrant and the fourth quadrant mapping to the second quadrant. And so these are mirror images across the origin. That's how we know that it's odd. Now, again, this is a lot of integrating you have to do. But again, the whole point is that if you're using only an odd function, then only the sine functions will survive the integration, and you won't have to deal with the cosine functions. Whereas if you extended this just with 0, for instance, you would have to deal with coefficients for both sine and cosine.